not read.
Okay, so welcome to our last lecture on group theory, essentially. But we have some homework to do. 2.8, number 10. There are two groups, subgroups of G that are normal. And we are to show that the intersection must be normal. And that's the correct statement of the problem. First, what do we know about the intersection, for sure? From previous work.
Well, that's what I'm both in there. Well addressed.
But what do we know? Yeah, it's everything in N and K. What is it? What kind of structure must it have before we start what we've already proved? It's a subgroup. Because, well, we proved that before. So I'm not going to go backward, but yes. N intersect K is a subgroup. And what are we absolutely sure is in there? The identity, right? So it's got at least the identity in there. So that's a starting place. So from prior work, we know at least that N intersect K is a subgroup. And E is in there. So to prove it's normal, what do we need to show? What does it mean to be normal? Not exactly. This is what it means to study. The definition of normality should be instant. It should be part of who you are at this point, just like the definition of subgroup and cyclic group. If you don't know the definition of normal right now, you're not studying sufficiently. What does it mean to be normal? Must be what? The right and left cosets must be the same set, right? That's what we need to show. We need to show. So how do we go about that? How do we show two groups are equal? They're subgroups of each other, right? So choose X in I need to show that it's in here, right? can I do that? Well, this means that x is equal to g times, let's call it y. And where does y live? It lives in n and it lives in k. So in particular, I know that this is an element of what set? Well, it's in G, but it must be in Gn, right? Because y lives in n.
Would it be in GK too?
It's also in GK. But what do we know about n? It's normal. So I know this equals what? G. So I know that x lives in mg. But gk is equal to what? G, because k, that's normal. So because x lives in G, and x lives in kg, where does x live? Implies x is an element of m intersect k, g, right? Because that's what that is. And a similar argument will take you the other way. That is, if I start here, I can kind of reverse the argument and go the other way. So that's how you prove. So what we've established so far is that, in particular, that G n intersect k is contained in n intersect k. G. And if we go backward by a similar argument, we could say where we start by assuming the element's in here and show that it must be in here by the reversing the flow of these arguments, we can show that n intersect k, G, lives in G n intersect k. Therefore, they're equal to each other. That's how I prove that any sets are equal. They're subgroups of subsets of each other. Therefore, because G was an arbitrary element, we can say, get our conclusion. That's actually a little misleading. To write it out fully, you have to write out the other reverse argument. This is a kind of problem that could easily appear on an exam. You should be able to work this kind of problem. Well, let's move on to some details out of the chapter. The other homework problem I'm going to post till Friday, because if you haven't worked this one, you almost certainly haven't worked the other one. I want it turned in on Friday, which is 2.9 1A. It's a lot of work. You're forming the center of the dihedral group, D6, of 12 elements in the quotient group. So if you haven't looked at that yet, make sure you look at that and get it, bring it to class on Friday. D6 is a lot easier to work in than D12. Okay, so what he calls factor groups, just to remind ourselves of definitions. And the operation of coset sin h defined by AH star BH equals A star B, the group operation applied to the elements. H is well defined. And makes the set of all cosets of H a group. With that as the operation, with H as the identity. And we've had this on the board, let's just do it again. How do I know H is the identity? Well, H is certainly the same as EH, right? Because the identity is in H. So those two are the same thing. So if I do A H times H, that's the same as doing AH times EH, which by the definition of my group operation is what? It's AE H, but AE is A, and that shows it's the identity, right? So okay, so that's definitional. The prototypical example. Let's do 11Z is a normal subgroup of ZY. Why is 11Z a normal subgroup of Z? What kind of group is Z? It's abelian. Every subgroup of an abelian group is trivially normal by the normal definition, right? So that's normal. And so if I form this set of elements, the cosets of 11Z, well, what would they be? It would simply be the set here, 0 plus 11Z, 1 plus 11Z, 2 plus 11Z, 3 plus 11Z, 4 plus 11Z, 5 plus 11Z, 6 plus 11Z, 7 plus 11Z, 8 plus 11Z, 9 plus 11Z, and 10 plus 11Z. There's the 11 elements, 11 cosets. Where to do the arithmetic, I simply add the representative of the coset. So 3 plus 11Z plus 4 plus 11Z is 7 plus 11Z. And 8 plus 11Z plus 7 plus 11Z would be what? 8? 4, right? Because 8 plus 7 is, last I checked, 5, is 15, right? Mm-hmm. So I did 8 plus 11Z plus 7 plus 11Z. That's the same as 8 plus 7, which is 15 plus 11Z. But how can I write 15? 4 plus 11, right? So that's 4 plus 11 plus 11Z. And what's 11 plus 11Z? 11Z because 11's in there, right? That absorbs it. So it's 4 plus 11Z. And we've just done mod 11 arithmetic. So this is why this whole idea was invented, kind of. So when you're doing modular arithmetic, you're really doing arithmetic this way. So what it means is if I choose any element in here, it acts like 0. 0, 11, minus 22, plus 55, etc. All the elements in here are multiples of 11, so they all behave the same way. And the same thing with 3 plus 11z, that's got 3 in it, it's got 14 in it, etc. All of those elements behave the same way. I guess I can always write them as 3 plus something times 11. Okay, so that's example and definition of a factor group. Okay? So this group with this identity is called a factor group by our textbook, or more standardly, a quotient group. And it's read the same way we read it here. G mod H. Because this is the basic idea of modular arithmetic in general. What does it mean? It means I'm declaring every element in here to be 0. Just like here, I'm essentially declaring every element in here to be 0. So it sucks up anything that looks like part of it. And so here, when I do G mod H, everything in H is 0. And so all I keep is the stuff that's left over. And I sucked out all the parts of an element that are already in H. So that's why it's called G mod H. Okay, so that's the definition of a factor group, or a quotient group. These have some properties. Besides the one we've identified, that the normal subgroup itself is the identity in the quotient group. Okay. Map from G to G mod H, call it P. I want to send every element of G to an element of this thing, so what would be the logical place to send little g to guarantee I get an element in here? I want to map from the group to the quotient group. Where should I send little g to guarantee that it's one of these things? Everything here is a coset, right? So I have to send it to a coset. What's the logical coset to send this to? A hard question. How do I form cosets? Where should I send the little g to make sure it's one of these cosets? Where? That would send everything to 0. So G. Of course, right? That is a homomorphism. How do we prove something's a homomorphism? I pick two elements where? Proving a homomorphism. Yeah, I need to pick two elements where? In here or in here? In G. Right? So choose A, B in G. Then I need to show that phi of A star B is equal to what if it's a homomorphism? Phi of A star phi of B. But what is this equal to by definition? Well, it's equal to A star B H. Right? But by the definition of operations on cosets, what is that equal to? Our very definition of the arithmetic of cosets. AH star AH. And what is that with respect to my map? This is phi of A, right? And that's phi of B. Therefore, phi is a homomorphism. An operation preserving map. Change this.